Organize a lecture today. Okay, so today I'm going to talk about efficient LLM solving using Lossy computation. This is a new concept proposed by my lab, and what we want to do is like, hopefully, because again, I want to emphasize, I want to do like this kind of use very easy, very simple techniques to solve real-world problems. That's why after having a good understanding of the whole system design, just with like a very simple math, with very simple equations, we will be able to boost the performance significantly. That's the intention, such that many of us can reproduce our results, and many of this kind of research outcome could be easily adopted by big tech. So that's the main purpose, and that's the philosophy of my research, at least. So, as we know, large language models, they are powerful, however, they are not ideal. We suffer from the problems LLMs, they may make up answers, well known as hallucination. Okay? There are two main reasons of behind this. One is like probably at the time of training the model, we didn't have the source information. And another reason is like at the time of training the model, we may only have outdated information. It was trained probably last year because it takes like a long time. Sometimes half a year for a new version. This is standard by Meta. Sometimes like 6 months for a new version to be released. That's why at the time of really, when we use the model, the information might be like 6 months ago or even longer, okay? So because of these two reasons, to answer this type of question, what are the symptoms of Ashcroft syndrome, which is a rare disease? At the time of training Llama 2 model, so probably there was no information. That's why Llama 2 70B was not able to answer the question directly. And just for the terminology purposes, so Llama 2, this is a version 2, and 70B represents the number of parameters of this specific model. And one potential solution is to serve with extra facts, and hopefully we can reduce the hallucination by consulting with the backend database, by providing the source from the facts, and to give the up-to-date information based on latest available data. The idea is like this. So we have a query like this: what are the possible causes of another rare disease? To answer this question, in addition to the query, in addition to the prompt, what we are gonna do is like to feed extra facts in terms of, for example, the papers from PubMed, some like textbooks, whatever information you will have at hand to feed into the large language model, and such that with the query, with the fact information, we will be able to answer the question effectively. And also, to reduce the hallucination, there are two main specific main techniques. One is called long context serving. I'm not sure whether you realized this or not in the slide we introduced yesterday. When we talk about Llama 1, 2, 3, one specific parameter we introduced was like, how many tokens? What is the context length of each of the model? So starting from possibly 1,000 tokens to like 4,000 tokens, no matter what. So the idea is like every single version of the released large language model, there is a context limit. And so when we directly feed it, later on we're going to introduce, when we directly feed too long context into this model, it will lead to some problems. But anyway, so the idea here is like we don't do much if the context information, if the extra fact information is not that long. We will be able to couple the prompt with some extra facts together to the large language model. Hopefully, we will be able to leverage the long context serving paradigm to answer our question. And another way is called RAG, retrieval augmented generation. The idea is like, probably the information is too much. It is a textbook containing like hundreds of pages of information, and only probably one small chapter containing 10 pages of information is relevant to our rare disease. And that's why what we want to do is like, firstly, we want to develop a search engine based upon the prompt, using the prompt as a query. we need to retrieve the relevant pages of information from the textbook, and we only make use of the 10 pages in combination with the prompt and feed everything to the large language model. And hopefully LLM will be able to answer the question very effectively. So these are two major paradigms we want to leverage to deal with the hallucination problem for now. We are facing several challenges. The first challenge I would like to discuss is the serving length limited by the pre-trained length. As we mentioned, for each of the released version, for example, Llama 1, 2, 3, 4, each of them, they are associated with the context length. That's why LLMs, they may fail when serving length is larger than the pre-trained length. Here's the context length I'm talking about. It is the pre-trained length. It means we have a context limit at the time of training the model. And because of the resource constraint, because of computational, because of the training time and many other constraints, we are not able to set up unlimited, too long context window at the time of training the model. That's why there is always a context limit. And from this figure, we can say X represents the relative position, and it means at the time of serving the model, the length of each of the testing data, and the y-axis represents the attention score. As we can see, when we try some testing data on the model, Llama 1, 7 billion parameter, and the 2K here represents the context limit. It means at the time of training the model, we only use 2000 as a context constraint. No training data was longer than 2000 tokens. Okay, so when we serve the model, and when we feed some testing data within 2000 tokens, the attention score tend to be very stable. It means it's working pretty well. Unfortunately, with the serving length, when we are feeding for example, some text information longer than 2000 tokens, like 3000 tokens, and the attention score tend to be very unstable and showing out of distribution. It means at the time of serving the model, because when we train the model, we have never seen any text information longer than 2000 tokens. That's why at the time of testing and serving the model, we are not able to, the large language model is not able to deal with some long context. So this causes a lot of problems. We're going to discuss later. And that's why almost at each model, large language model release, they want to emphasize, we can deal with 1 million tokens, we can deal with 500,000 tokens. This is one of the probably most important parameter each of the team would like to discuss at the time of releasing the model. And the second challenge, significant challenge we want to discuss is serving length limited by the available memory. As we briefly touched yesterday, GPUs are extremely expensive and valuable resources in the large language model age. So what are the main reasons? Large language models, they need to cache intermediate state known as KV cache. We briefly touched this yesterday of all of the tokens. So KV cache grows with the context length, and will be the new bottleneck of GPU memory. Let's take a look at these two pie charts. Okay, the first one is when we deal with this is a profile. This is the profile results based upon Llama 270. Okay. When we serve the model and deal with text information within 500 tokens, okay, the model occupies, it means the computation expenses occupies 98% of the memory. And the model occupies 98% memory. And the KV cache only occupies 2%. Okay, pretty good. Because essentially we consider GPU is a computational resource, right? It's not a storage resource. That's pretty good. We made a very good use of GPUs. Okay. Unfortunately, when we are dealing with long context, such as sequence length over 100,000 tokens, it's pretty long. The KV cache occupies 78% of the memory. It means with the growth of the serving text length, the GPU memory, unfortunately, it becomes, a very big burden in terms of memory. And we have to chase like larger and larger memory. And this is not our original intention, which is supposed to be used for computation and calculation, right? So that's why we're not even talking about what if like we want to serve some like sequence length longer than 1 million tokens. That's a disaster. That will be a disaster. Very limited resource in the GPU will be used for computation purposes, and the majority will be used to store the intermediate state, unfortunately. And at the same time of seeing some challenges, we did observe some opportunity. It's called Lossy computation, and this is probably the philosophy of designing most of the efficient algorithms. So how to understand this? The key idea is like LLMs, they only need a large scale but lossy computation. I would like to show two examples, but there's no quantitative results to demonstrate this, but I would like to show two examples in the history. The first one is like, this is a study to compare two different types of models. The first model is like the precision. Remember when we discussed quantization yesterday, we talked about the precision of the weight, right? So if we use 8-bit to represent the weights, and we have 14 billion parameters. And another model is like 16-bit, higher precision and with a lower number of parameters. Essentially, these two models, the memory cost is very similar to each other. And by comparing these two models, we can say the first model achieved much higher performance, much higher accuracy, and it achieved a better performance. And this demonstrates like we don't really need that accurate, that precise representation of all of the weights. Rather than we would prefer larger number of parameters. Okay, that's why larger model tend to have like advantage of doing the computation. And another, so these two results were reported by these two papers. And you can see certainly like first paper, they were reported in the two papers like respectively. And the second one is like very similar to the paper we discussed yesterday at the beginning of the algorithms. So basically, we want to remove some of the nodes, neurons, some of the paths in the deep neural network. And it achieved sometimes even better results comparing to the original state model. So seeing these two examples, we would like to conclude. So the first one is under the same memory. Large language models prioritize scale over precision. Very interesting observation. Okay, we don't really need a 32-bit, 16-bit to represent the weights, and can we do even more aggressively? Like does like 4-bit work? Does 2-bit work? Does 1-bit work? So these are the research questions we would like to answer. And the second example is like drop out this kind of removal of neurons and pathways. They improve the performance by randomly masking out some parameters. So very interesting observation, okay? And based upon this philosophy, we wonder whether or not we really need an accurate representation of the model, whether or not we really need the full model. Can we quantize the model to make them smaller? Can we remove some of the weights, activations to make them like smaller? So how we are gonna do that? And how to make the trade-off? How to design corresponding algorithms of doing so? So basically, based upon the insight, LLMs only need large-scale but lossy computation. I would like to introduce some like long-context algorithms from algorithm perspective, as well as some like system support, and showcase some application at the end of the talk. Some preliminary information. So one of the 5 key elements we introduced yesterday about transformer is about positional information. Okay, positional encoding. So here I'm going to very quickly review the relative position information in large language models. For example, I love machine learning, and each row represents the position of these 4 tokens in this context, and each column as well, from 0 to 3. And each number here, each cell represents a relative position between, for example, merchant and lab is 1. So encoding the relative position between 2 tokens in this context information. So it means how close they are, basically. And the large language models, they cannot generalize across lengths. They may fail on long context due to the auto-distribution issue. And here is a toy example. In this toy example, the pre-training context of Windows 7, meaning like at the time of training the model. So this is a toy example, okay? This is a fake example. So at the time of training the model, the orange region represents the large language model only see some like textual data within 7 tokens. That's why they will be able to understand in terms of the positional encoding, because they will see this positional encoding. Remember, so how we make use of positional encoding? It will be like it will be added to the original like token embedding together. That's why they will be seeing like the numbers from 0 to 6. Unfortunately, if we train the model within the context of Windows 7, they are not able to deal with any information like 7, 8, and 9. Because at the time of training the model, they have never seen this. Machine learning models are very smart. They can deal with a lot of information. Unfortunately, sometimes they are very naive. If you didn't see them at the training time, they are not able to do it at the testing time. That's why in this model, when the input length is 10, unfortunately they may fail. They may go out of distribution. As we see from the results, the attention score may be very unstable if the serving length is longer than the training length. Oh, sorry about that. So here I will make use of the terminology inference, serving, testing interchangeably. But essentially, at least in my talk, they mean the same thing. The testing, inference, serving. Okay, they mean the same thing. And one idea is like, you can see how simple the ideas are. Okay, very, very simple. One idea is like, okay, lossy position information, probably they may be enough. The exact position of the distance token doesn't matter. Lossy information should be fine if it can maintain the order of tokens. Thinking about how human beings predict the next token. When we write an essay, to write the next token, do we need to remember the exact position of one token appear like 1,000 tokens away or like 900 tokens away? So in most of the cases, it doesn't really matter. As long as we remember, okay, some time ago, I wrote some like context like this. That will be sufficient, right? That's why the philosophy of the lossy information here is like, we do not need to, the model, human beings, as well as the large language model, they do not need to really remember the exact position. So sometimes rough, very blurred information, okay, it happens like 5 tokens away, 500 tokens away, as long as we are able to distinguish some nearby tokens, some far away tokens, that will be good enough. That's the philosophy how we design this kind of algorithm. And to do this, we will say, okay, sure, you have never seen tokens like indexed by 7, 8, 9. How about we just group them together? Meaning like for the first tokens, we just label them as like position 0, and then position 1, position 2. Then the 10 tokens will become like 5 relative positions, starting from 0 to 4. Ha, problem solved, right? Because at the time of training the model, we have seen like the information starting from 0 to 6. 7 tokens, 0 to 6, yes, 7 tokens. But now, the position information is within like, let's say, it is 5 at most. That's why we will be able to deal with, like 10 tokens. Previously, we cannot Previously, we are not able to process this because it is over the context window. But now, with a very simple operation, by grouping them by 2, we will be able to deal with them. So that's the basic information of how, that's the basic idea how we want to group them together and deal with the long context information with this very simple floor operation. Any questions so far, by the way?